NAS started with the same concept I wanted to talk about. Whenever you hear topological phase, I mean, the word topological in a physical context, especially with the quantum information / many-body context, you can always associate some complexity. So let's imagine that we have a local circuit. I assume you all know what the local circuit is. There's some Euclidean space, the L by L by, d-dimensional Euclidean space, and we have a metric on it, and each gate is locally acting, geometrically locally acting on that. So just imagine some circuit. It can be deep, it can be shallow, some circuit. Now, ask yourself, can you define a circuit on an infinite lattice such that it obeys the same periodicity as in your previous compact periodic lattice? What's your guess? It's an easy question. Trivial, yes. Why? Well, let's think about the layer by layer. Imagine we have a circle, that's my lattice, and we have 5 gates that are all parallel. And then you just unwrap that circle and place your gates accordingly, and that's it. That will compactify to your original circuit. Next question. Can you match the action of the circuit? Here, the action means that, what's the purpose of circuit? It exists to conjugate operators in the Heisenberg picture. So can you match the action of the circuit, original circuit? Yes or no? Yes. No. But yes, if the circuit is shallow, so that the nominal light cone is small, then the circuit is not making use of the boundary condition, so the action should match. Now, a slightly different question. Can you define? I want to lift the circuit in my complex circle or any other torus. I wanted to define similarly acting thing, a unitary, gigantic unitary, that is whose conjugation action is exactly reproducing what is given at my compact space. Is it yes or no? Again, no, but yes, if the original circuit in my compact space had a true small light cone. Here, I'm distinguishing between the nominal light cone versus true light cone. True light cone means that it is defined by the action. You bring a local operator and you conjugate it, and it produces some operator, and you look at how large it is. And nominal light cone is a geometric thing that you would draw in your circuit diagram. So if your true light cone is small, then there's no problem defining the action on the infinite lattice. Now, I want to mix these two last questions. Can you lift your circuit in such a way that it matches the action? And how does it play? That's the theme of this talk. So, and for that, to discuss that, there is a useful notion called QCA. There's a historical reason people call it QCA. It is designed, well, this first discussed as a model of computation, and then people wanted the reversibility, and because of the physical relevance, people wanted the locality, and that's the definition we are going to use. Okay, so what is QCA? It's a locality-preserving unitary. If you are a true mathematician, then you may object I call it unitary, but let's put that aside. So it is an automorphism of the operator algebra in your whatever system you have. Automorphism means that it preserves the multiplication and addition, and I demand that the inverse exists. And there's an important notion of locality preserving. So namely, if you act on some local operator x, and you examine how large this operator is, then that support must be contained in some small neighborhood of the original operator support. That's my requirement, and that's what I mean by locality preserving. Examples, of course, is small depth quantum circuits, in 1 or 2 or any dimension. And if you allow your tail, then short time evolution of generic local Hamiltonian fits into this definition. I want to emphasize again that the support condition is really important in all discussion of this, because if you forget it, then any infinite lattice are isomorphic to another by some unitary. And that unitary violates the locality preserving criteria. Why do we want that? Well, it includes the most important circuits that we know. Now, let's think about it slightly. Let's make the connection between the QCA as a general automorphism versus the quantum circuit that we are more familiar. And here comes the dimensionality. Imagine you have a circuit. Here I drew just one dimension, but you should think about all the other directions are now suppressed. It's just the one dimension I draw. And if you had nothing, then of course the empty circuit implements identity. But you could implement identity after apply a certain number of operations, gates. So your circuit may be non-empty, but still may be implementing identity. It does nothing to your operator algebra. Now, what's nice thing about the quantum circuit is that you can erase your gates. There's no trouble defining, a circuit that looks like this. I just literally erased the circuit on the left-hand side. On the left-hand side, I would have by trivial reason, I will have identity action. And deep in the bulk on the right-hand side, I will have an identity action because of my assumption that the overall circuit is doing identity. At the boundary, something is happening. And this something has one property that since it comes from the small depth quantum circuit, it must be preserving the locality. But otherwise, it is pretty general. Which may be surprising fact. This alpha is sandwiched between identity and identity. So you may think that this must be another circuit that implements something else. But it turns out, that's the main theme of the talk here. It may not be a circuit in the infinite lattice. Yeah, so this is going down in dimension. I started with a d-dimensional circuit that is non-empty but identity circuit. And then I induced some boundary action by dropping the gates. And this alpha lives in one dimension lower because it lives on the boundary. You can go back. Starting with some alpha, a QCA lives in the d minus 1 dimension, then there is a simple argument that shows alpha tensor acting on a separate system, alpha tensor alpha inverse is again a circuit of small dimension if alpha is locality preserving. Then using that fact, you can construct a circuit in one dimension higher in such a way that at the boundary alpha is induced. How do you do that? It's called the Swindle argument. You create a alpha and alpha inverse pair here, and the same pair here, and so on. And then you annihilate the different pairs, one shifted. This is exactly the same as you're inserting a billion NE into the bulk instantaneously. And this has a very close relationship with the now very mature subject of short-range entangled states. So it comes with different names, but short-range entangled states is one name. Another name is what is called invertible states. Then the definition is as follows. Psi is called invertible if there exists some other state, which I denote as inverse. It doesn't mean that you can invert a state, it's vector. Some state called inverse, such that the joint state can be prepared from the product state by some short depth quantum circuit. It has a very fast decaying correlation, so it is called short-range entangled. And such a state can be obtained by the same tight lines of argument. It can appear as a boundary state of one dimension higher preparation circuit. And given any such invertible states, you can realize a circuit that prepares it at the boundary and in one dimension higher using the same Swindle trick. All right, example. So here is a two-dimensional lattice. There's a two-dimensional lattice, and it has a four-step locate type evolution. In the first step, only the green edges are turned on, yellow, red, and blue, and so on and so forth. It goes all around and round, but the interaction is tuned such that after one step, the two states that are coupling are just swapped. And after 4 rounds, the state at the one side, deep in the bulk, is coming back to itself, so it does nothing in the bulk. But at the boundary, because of the lack of any neighbor for certain interactions, the boundary states are now transferred along one direction. So I managed to implement identity circuit in the bulk, non-empty, and induces some non-trivial action at the boundary. And in this case, that non-trivial action is the translation. Okay, so up until 2018, that translation induced by a one-dimension higher circuit was the only example. And we discovered some other example that is not shifting and is not a circuit, but is locality preserving in the infinite dimensional lattice in 3 dimensions. And the construction is basically brute force calculation. You might want to read that, and you may think, oh, the font is too small. How can I read that? Then you get the point. There is a construction, but you don't want to read it. It's too long. It's explicit. You can calculate about it. You can do everything, but you don't want to read it. But basically what it does is the following. It disentangles certain symmetry protected state in 3+1 dimension. And it disentangles in a so strong way that it not only disentangles the ground state, but it also disentangles the entire spectrum for a particular choice of the Hamiltonian for that state. And the result of this paper, which is not the paper I'm talking about for this QIP talk, the result of this paper is basically this theorem, assuming that no commuting Hamiltonian may implement a theory that is chiral, then this construction gives a locality preserving unitary in 3+1 dimensions that is provably not a quantum circuit of finite depth circuit. And that translates to the circuit complexity question. This is a specific instance of translation invariant, a family of circuits, circuits whose true light cone is small, but if you were to implement it using local gates, your depth must be linear in system size. Typically in computer science, you want to prove a lower bound on the circuit complexity. Generically, almost all circuit has a deep depth. But if you ask that question for a specific one, it is extremely hard. This is the one instance you can actually show it. Well, with the one caveat that we assume this, which we believe to be true. Okay, let's specialize to a more manageable category, the Clifford category. What is a Clifford? For this audience, I don't feel I have to explain, but let me put it anyway. So I consider the Pauli matrices of a prime dimensional qubits. So this is a clock, shift variable, and the phase factor, the Fourier transform of it. And they obey the commutation relation up to a pth root of unity. And for technical reasons, P is taken to be a prime. And it has many uses in the conceptual world of physics as an error correcting code, as topological order, some self-correcting memory, partially. And we use it to wonder about black holes too. And the Clifford transformation is defined to be one that maps a Pauli operator to a tensor product of Pauli operators. Now, here comes the result. So I consider infinite lattice. Well, infinite might scare you, but it's actually simpler to think about infinite lattice. And then I put prime dimensional qubits at each site. So each site will be occupied by some prime power qubit. And then I consider the set of all QCA such that it is Clifford. It maps a Pauli operator to another Pauli operator. That's it. Now, locality preserving property is implemented. So every local operator is now mapped to a finite tensor product of Pauli matrices whose size is uniformly bounded across the lattice. And the result is that the group of such QCA, well, QCA is after all automorphism, so they form a natural, they come with a natural operation of composition, so it is a group. Now you mod out by a subgroup consisting of Clifford circuits, because I'm considering Clifford QCA, and also I mod out the translations. Then you are left with some smaller group, and you ask what that is. And the result is that depending on the spatial dimension, there are only these. They're not that large, surprisingly. And there's a pattern. For the oddest prime 2, there is a non-trivial element at dimension 3, but nothing below. And there's a periodicity 2 in dimension as you go higher. So dimension 1 is exceptional. For odd primes, not the oddest prime, you get the true periodicity of 4 in dimension, and the group is either Z4 or Z2 cross Z2, depending on the residue mod 4. If you focus on the most realistic dimension of 3, so here's a Z2 and Z4 and Z2 cross Z2, but the P is arbitrary. So if you enumerate all primes, then I get a gigantic group. And this group makes sense because whatever QCA you give me, I cannot map a Q bit into Q trit, say. The other direction doesn't work either because the simple matrix algebra in 2-dimension cannot be mapped onto 3-dimensional matrix algebra, and vice versa. So in that dimension, I discovered this infinitely generated group, but this looks familiar to some mathematician. This is precisely, modulo one caveat, what is so-called the Witt group of metric groups. So you endow certain quadratic form on the abelian group, and you consider the non-degenerate quadratic forms, and you mod out by hyperbolic forms, then you are left with these. And in a more physical term, these groups are precisely the abelian N theories modulo whatever you can obtain from quantum double construction. So it is a bit of a surprise. I worked on the assumption doesn't mention anything about the NEN, it's just the infinite lattice with the Clifford map. And surprisingly, at dimension 3, the NEN 3 at 2 dimension appears. One slide for how the argument goes. So first, I use the Hastings use of Kirby's torus trick. This is a trick. This is not a one theorem. It's just a theme of argument that reduces some possibly aperiodic problem into periodic problem. So it allows you to focus on the only translation invariant case. And there is a nice language in that translation invariant case applied for Cliffords and Paulis using Laurent polynomials, basically the group algebra of translation group. And then you study some surgery theory in topology, primarily, a part of the surgery theory pioneered by Nowicki-Wranitzky is all about quadratic forms. But it turns out that every element in that theory has a correspondence in the Clifford language. And one of the useful theorem there is that you can descend in dimension and giving rise to some certain isomorphisms as you go down the dimension. At the d-dimensional, you get the correspondence to the Clifford QCA. One dimension lower, you get some anti-Hermitian form. Another dimension lower, there's something I call lambda plus unitary. It's a unitary with respect to a certain quadratic form. And you can go dimension 1 more, and you get not anti-Hermitian, but Hermitian form. And for dimension 3, it happens to be related to the topological spin of anions. And you go back, d minus 4, you come back to this lambda unitary again, and you just inductively go down to 0 dimension, at which point you just calculate by brute force. Okay, so this is a one instance in topological phase business that something non-trivial is pumped through one dimension higher space by what we call trivial. So if you consider invertible state or short-range entangled state, this is swept through one dimension higher, giving rise to a path of trivial states. Locality preserving automorphism, or QCA, is swept through the one higher dimension to give a non-empty but identity implementing circuit. And specializing into the Clifford QCA, there was a dimensional descent procedure that was technically very helpful. And I suspect there should be a corresponding thing in a more general setting, which I am very interested to find. And one advertisement is that I found another very closely related object in one dimension lower, which I call invertible subalgebra. I wish to have another occasion to talk about that. And my thanks goes to my previous, there are several papers in this line of work. Lukasz Witkowski, who was a visiting researcher with us at Microsoft, Friedman, Hastings, and Wang are all Microsoft. So I thank them. And I will take questions. Thank you.
That's Jeongwan. Thanks for this beautiful talk. Are there questions? I see one here.
Thank you for the nice talk. I have a very basic question. So, what are the objects and morphisms in the Clifford category?
I said category, but I didn't mean to be the algebraic category in a precise sense. It's just a collection of things that smells like Clifford.
Okay.
Yeah, I said Clifford category, but it doesn't. It has nothing to do with the fusion category or braided category. Yeah.
Okay, thanks.
Does the higher Clifford gates show up anywhere in higher dimensions or anything? Have you thought about this?
Higher Cliffords?
Unitaries that conjugate Cliffords to...
Clifford hierarchy.
Clifford hierarchy.
Well, not yet. This one, the missing piece of Z8, it's the construction of Z8 vector is out there, modulo some conjectures, but the calculation makes use of such a hierarchy, although not too explicitly. Yeah, that'll be interesting to explore that. Yeah.
So if you apply your non-trivial circuit to a quantum state, what kind of entanglement do you generate if you apply this to a product state?
It gives a short-range entangled state because the alpha and alpha inverse are always a circuit, so it fits exactly to the definition of invertible state. So it generates a particular subset of invertible states. The exact scope is under study. In particular, we suspect that all the Waka-Wang models, Waka-Wang ground states in 3+1 dimension is disentangleable by strict locality preserving QCA, but that's still conjectural. Yeah.
If we put P equal 2 and D equal 3, and I come to you with some QCA, how can you decide whether it's 0 or 1? Can you look at it, and is there some kind of understanding of the result?
I interpret that question as how to diagnose the index of this.
Yes, thanks.
The proof is actually constructive. Every step is so. Starting with the specific QCA, you can go down to find various things, and you will reach the zero dimension. So it's a really mechanical calculation in the end. However, it doesn't apply to most general QC you want to consider. It only applies for Clifford case.
But how can it be a calculation if it's infinite? I have to give you infinite data.
So right. So there, if it is translation invariant, then you can encode all the information in terms of Laurent polynomial, and there you can start the calculation and you can program it. If it's not periodic, you can apply the constructive version of the torus trick, and then you turn it into the translation invariant case and do the calculation. So, but it is not entirely satisfactory. It involves two, it's too tautological in a sense, and the diagnostic of the bulk invariant is, I think, is an excellent question. This is an instance of complex states or unitary, and for truly intrinsically topological ordered states, we do have certain diagnostic that applies in the bulk. Here, we don't. So that's another research question.
Yeah, I actually have several questions, but thanks for the nice talk first. But my first question would have related to Frederick's question, which would have been, can you write down invariants? Is there something like, I mean, it's all the standard questions. Which perturbations is your classification invariant against? Is there some bulk edge correspondence thingy you can prove?
Right. Well, I interpret that as you called it topological, but what is topological about?
Exactly. Yeah.
Simple answer is that you consider the object up to quantum circuit deformation, which is precisely the perturbation you allow in the topological states. By demanding the gap preserving, you're essentially disturbing the state up to quantum circuit. And the same criteria is now migrated over to this unitary setting. Oh, yeah. Okay.